This is MAT 175, Lesson 16, Section 5.2, and our lesson is on one-to-one functions and inverse functions. Okay, determine whether a function is one-to-one. First of all, in order to be one-to-one, it has to be a function. In other words, it would have to pass the vertical line test. So remember, a function is for each x, there's only one y. So for this first one, for each x, that x only has one y, that x only has one y, that x only has one y. So we would say that's a function. And same thing here. This x has only one y, this x has only one y, and that x only has one y. But this x has two y's. So that one's not a function. This one is a function, this one's a function, but first one's a function, second one's a function, but the third one is not, because this x has two y's. Okay, so for a function, for each x there's only one y. But in order to be one-to-one, for each y you can only have one x. So this would be not only a function, but it would also be one-to-one. Okay, and so this one here, this is a function, but for each x there's only one y, but the question is, is there for each y only one x? Well, this y has two x's. So even though it's a function, it's not one-to-one. Okay, so we would say that's not one-to-one. And if it's not a function, it's not even going to be a one-to-one. So with it not being a function, that eliminates it from not being one-to-one altogether. Alright, here we have determined whether the following functions are one-to-one. Again, for each x there's only one y, right? But is it one-to-one? For each y there's only one x. Well, this y has two x's in it. So even though it's a function, it's not one-to-one. And here, for each x, there's only one y. So there's only one -2, no other -2's. So this -2 has a 6. But there's no other -2's that have another y value. And here we have a -1, does not repeat. 0's do not repeat. 1 and 2's don't repeat. So it's a function, but is it one-to-one? So in order for it to be one-to-one, the y's cannot repeat either. So this is 6, 3, 2, 1, 5. So the x's don't repeat and the y's don't repeat, so therefore it is one-to-one. Each x has only one y and each y has only one x. Okay, so one way you can tell graphically if a function is one-to-one. Now remember, to test vertically, to test if there's a function graphically, we use the vertical line test. But to test if it's one-to-one, first of all, we have to assume that it is a function. If we're testing if it's one-to-one on a graph, so we would apply the vertical line test. And I mean the horizontal line test. The horizontal line test, if the line passes through only one point, then it is in fact one-to-one. Well, here for parabola, the horizontal line test passes through 2 points. So even though it's a function, it is not one-to-one. Okay, for each function, use the graph to determine whether the function is one-to-one. F of x equals to x squared. That's going to be a parabola, right? Is that going to be, it's a function, but is it one-to-one? Okay, and you should have said it is not one-to-one. Okay, cube, it's going to go up and to the right, down and to the left. Is that going to be one-to-one? And you should have said yes, it is one-to-one, because no matter where you draw the horizontal line, the line only passes through one point. So, in fact, the x cubed is a one-to-one. Determine the inverse of a function defined by the map or set of ordered pairs. Okay, suppose that a graph is one-to-one, and then for each x, the domain, there is exactly one y, and for each y, there's only one x. So the domain for the function is going to be the range for the inverse, and the range for the function is going to be the domain for the inverse. So, and the reason for that is because for the function, you're given a function, the x and y coordinates are going to switch places. Okay, for example, here we have a set of ordered pairs of coordinate points. So your x's are -5, y is 1. And so for the inverse, you're going to switch. What was the x is now going to be the y, and what was going to y is going to switch with the x. So the inverse is going to have 1, -5. Okay, now for 3, 3, that's going to stay 3, 3 because they're the same, and 0, 0, that's going to stay to 0. So here's our function, 2, -4. So the inverse, the x and y switch places, and that'll be negative. The inverse will have -4, 2 for its coordinates. And here's 7, -8. Our function, our coordinates for our function. Inverse is going to be what? -8, 2, 7. -8, 7. So the domain for our function is all the x values. -5, 3, 0, 2, 7. Okay, and the range are going to be all the y coordinates. 1, 3, 0, -4, -8. So what was the domain for our function is now the range for our inverse. And what was the range for our function is now the domain for the inverse. Well, that makes sense because for the function, the x and y switch places. So of course the domain and range are going to switch places too between the function and its inverse. So here's our domain for our function. Here's our range for our inverse. Okay, they're the same. And so our domain for our inverse is going to be the range for our function. So our domain for our inverse is going to be -8, -4, 0, 1, and 3. Okay, now here we want to verify that g of x equals to x cubed is the inverse of g of x is cube root of x. And what we do here is we are going to, so we have g of x. We're going to show you here on a blank piece of paper, blank sheet. Okay, here we have g of x, and that's equal to x cubed. And we have its inverse of g, and that's equal to the cube root of x. And so we want to show that they are inverses of each other. So we take f, so in other words, we take g of its inverse of x. Okay, so that'll be g of inverse of g of x. So basically we're taking the g of x, and it's like we're cutting that x out, and we'll put parentheses there. Okay? And so this will be parentheses q. Now we're going to take the inverse, and we're going to put that in place of where the x was. So this would be the cube root of x. And we know that the cube and the cube root, they're inverses of each other. They cancel out. And all we have left is x. And so if we did the same thing with the inverse of g of x, so that'll look like this, of g of x, right? Basically we're taking the inverse and we're cutting that x out. Cut the x out, cut the x out of there. And so that would leave us with cube root and then parentheses. Okay, and now we're going to put in the g of x in there. Well, g of x is x cubed. So again, the x cube root and the cube cancel each other out. They're inverses of each other, and all we have left is x. And so that's a way that you can check to ensure that whatever you find for your inverse is in fact the correct, what you should have. And so that's what we have here. Here we want to verify that the inverse of f of x is 2x plus 3, and its inverse of f of x is 1/2 x minus 3. So we want to check basically that they're inverses of each other. So this one, they have the inverse of f equals to f of x. Well, the inverse of x is going to be 1/2 x minus 3. So we cut that x out, put parentheses. Okay, and so that's what this is here. This is up here. We cut the x out, so this is 1/2, and then x, where the x was, we put parentheses, and then we're going to put the 2x plus 3 in there. Well, the 3's, they're additive inverses of each other. They cancel out. And so that leaves us with 1/2 times 2x. The 2's cancel out because they're multiplicative inverses of each other. And we just get x. So now, if we do it the other way, f of its inverse, now we're cutting that x out for the function. And now this would be 2 parentheses x plus 3, and where the parentheses is, we put our inverse, 1/2 x minus 3 in there. Well, the 2's cancel here. And that leaves us with just x minus 3 times, plus x plus 3. And the 3's, they're additive inverses, they cancel out, and we just get x. So we can say, yes, in fact, f and its inverse, its inverse of x are inverses of each other. Okay, verify that the inverse of 3 over x plus 5 is the inverse of f of inverse of 3x minus 5. Okay, so we're going to start with our inverse. Okay, so here, what we do is we take our inverse, okay, cut that x out here. And we're going to cut this x out here and put parentheses. So that'll be 3 over, and then where the x was, we put parentheses, because it's like a hole there now. And now we're going to take this f of x, and we're going to put that in there in place of where that other x was. So this would be 3 over x plus 5. Now remember when we did this, a over b equals to a divided by b equals to a times its reciprocal of b. So here, this would be like saying 3 over 1 and here this will be divided by 3 over x plus 5. So we're going to take that second term and we're going to apply the reciprocal. Multiply it. So what was x plus 5 in the denominator is now x plus 5 in the numerator. And what was in the numerator 3 is now in the denominator. So this is 3 over 1 times x plus 5 over 3. And so the 3's cancel. So basically what we're doing here is we're taking the 3 and we're flipping that denominator, right? We're applying the reciprocal to that denominator. And so this is 3 over 1 like that. And so the 3's cancel, and we get x plus 5 minus 5, and so we just get x. And so we can say that f of inverse are in f of x fact inverses of each other. And that's what we have here. And so with that, we can say that here we cannot have x cannot be, because we would get an undefined for our function, right? We would say that x plus 5 equals to 0, so x cannot be negative 5. And so we could apply that down here too. We cannot have negative 5 here because that would be undefined. And that's what this is. Note the domain of f is cannot be negative 5. Domain of g cannot be 0. Alright. And so that's what we did here. We flipped it, and then the 3's canceled, and then you got a positive 5, negative 5, and x equals to, it's just x left over. Now for f of its inverse, we're taking f of x, right, where this x was, we're going to cut that out, and we're going to put this 3 over x minus 5 in there, and that's what this is. Well, in this case, we know we can simplify that a minus 5 and a plus 5, they go to 0. So now that just leaves us with 3 over x, so we just flip or apply the reciprocal to that denominator, and that gives us 3. That would give us 3 times x over 3. And so the 3's would cancel, and that's why we just get x. Okay, so we've proven that f of its inverse is also, they are inverses of each other. Okay, obtain the graph of the inverse function. Okay, and the way to do this is, you see this line right here, this y equals x, that's known as the axis of symmetry. So wherever the function crosses that axis of symmetry, the inverse will also cross it. That's one thing to keep in mind. Another is that whatever your coordinates are for your function, your inverse are going to be switched between the x and the y. So here we have a is x, x is a, and y is b. So we switch those two, and now for the inverse, x is now the b and y is now the a. And you're going to do that with all the points between the function and its inverse. Okay, the graph of function of f and the graph of inverse of f are symmetric with respect to the y equals x line. Alright, so here we have a1, b1. So that's the blue is our function. Okay, y equals f of x. The red is our inverse. So we start by drawing your function, and then you pick some points. Like some good points are the x and y intercepts. And now notice where this blue line crosses the axis of symmetry, the inverse also crosses at that very same point. So anywhere the function crosses the axis of symmetry, the inverse will also cross at that same point. So here we have a1, b1. So for the inverse, you just switch the x and the y, and now you have b1, a1 for the inverse. a2, b2, switch that, and it's b2, a2, and so on. Now notice, wherever the function moves away from the axis of symmetry, the inverse will also move away. As the function gets closer to the axis of symmetry, the inverse also gets closer. So here this moves away, this moves away. It gets closer, the inverse gets closer. And then here it kind of moves away a little bit. You get this bump here. Well, the inverse gets a bump, but in the opposite direction. And then here, the function gets closer and then crosses your axis of symmetry. Here, the inverse gets closer and crosses the axis of symmetry the other way. And so this is your function and your inverse in relation to the axis of symmetry. So here graphically we have the original function is x cubed, and that's what this is here, x cubed, up and to the right, down and to the left. So if we were to draw this, let's say we'll draw the y equals to x cubed in red. Okay, now the inverse is going to the inverse, which is the cube root of x. We'll draw that in blue. And so here, as the function crosses x of symmetry, so does its inverse. So here's your x cubed, kind of looks like an S looking graph. And so this would be the cube root of x. And notice, wherever the function crosses the axis of symmetry, so does its inverse. Alright. Same thing here. Function crosses the axis of symmetry, so does the inverse. Okay. Alright. So at this point, here we have a function. We'll call this y equals f of x. Okay, so this first one is negative 2, negative 1. So the inverse would be negative 1, negative 2. So here's negative 1. This is negative 2, negative 1. So the inverse would be negative 1, negative 2. Negative 1, negative 2. Okay, so the inverse is in red. Here we have negative 1, 0. So where would the inverse coordinate be? You should have said 0, negative 1. Alright, and now the third one, 2, 1, where is the inverse for that? And you should have said 1, 2. Okay, so it's going, in the axis of symmetry, I'm going to draw that in black. That's going to be negative 1, negative 1, negative 2, negative 2, 0, 0, 1, 1, and 2, 2. So it's going to look, I don't have a ruler, so I'm going to draw this as straight as I can. And so your inverse is going to come up and then cross right where your function crosses, and then comes up. Okay, and so this would be your inverse. Y equals to your inverse of x. Okay, and so that's what we get here. Alright, and so we can see that in this case the line is parallel. The function is parallel to the axis of symmetry, and so is your inverse is also parallel to it. And then they both cross at the same point, and as the function moves away from the axis of symmetry, so does its inverse. Okay. Alright, here we want to find the inverse of this function. Okay, our function is f of x, and so we want to find the inverse of that. So basically, what I like to do is, since we know that y equals to f of x, we replace f of x with y. And so this will be y equals to 2x plus 3. So the next thing we're going to do is we're going to switch places with the x and the y. So now this becomes x equals to 2y plus 3. So we switch places with the x and the y, and now we solve for y. So we apply minus 3 to both sides, and we get x minus 3 equals to 2y. And then we divide by 2, and divide by 2 here. And you could, here we have y equals to, and we could write this as x minus 3 over 2, or we could write it as 1/2 x minus 3 over 2 like that. And so that would be our inverse function, equals to 1/2 x minus 3 over 2. And that would be our inverse. Okay, and so step 1, replace f of x with y, and then we go ahead and switch places with the x and the y, and then we solve for y. And so we applied minus 3, and so that becomes x minus 3, and that's what that is. And then divide by 2. Okay, now they put 1/2 in parentheses, x minus 3. But if you had it as x minus 3 over 2, or you had it as 1/2 x minus 3/2 x, it's all the same thing. Okay, and so that's your inverse. Okay, so to check it, you do that f of its inverse, or its inverse of f. And so that's what we did here. We took our inverse, took x, cut the x out, put parentheses, and that's what we did here. And then we substituted the original function, 2x plus 3, in there for x. The 3's, you got a plus 3 and a minus 3, they cancel out. And you get 1/2 times 2, and that just gives you x. Alright, and then the other one is taking the 2x plus 3, cut the x out, and you put the inverse in there. That's what this is. The 1/2 x minus 3 goes in there for the x. And so basically this is just a review. You take your y, substitute y in for f of x, switch your x's and your y's, and then so on, and solve it for y. And then to check, to verify that your function and your inverses are the same, then you would use the f of inverse of f of x, and you should just get x. And the same thing for f of its inverse, you should get x again. Okay, here we have the function f of x, and we want to find its inverse. So basically we're going to substitute y in for f of x, and then we're going to go ahead and switch places with the x's and y's. Well, here there's 2 x's and only 1 y. Well, when we switch places with the x's and the y's, now there's only 1 x and 2 y's. Now we have to multiply this y minus 1 to both sides. We got to get that out of the denominator, and that's what they did here. Okay, you got to get that denominator out, you got to multiply it to both sides, and that's what we did here. So the y minus 1s, they cancel on the right side. Well, now what you have to do is you have to distribute that x. So this will be xy minus x. Well, the problem now is you got y's on 2 sides of the equation. Well, you don't want 2 y's on 2 sides of the equation. You want y's, you got 2 y's. You don't want 2 y's, you only want 1 y. So what we have to do is we've got to get the y's on the same side. Well, how do we do that? Okay, you should have said you're going to apply minus 2y to both sides. And then you're going to move this x over, so you're going to apply a plus x to both sides. And that's what we did here. So the minus x plus apply plus x, 1x to both sides, and then you apply minus 2y to both sides. Well, you still have 2 y's. So how do we go from 2 y's to 1 y? What can we do? Well, you should have said we can factor the y out, because the y is a common factor. So we factor the y out, and that leaves us with x minus 2. Well, we need to isolate the y now. So now what do we do? Well, you should have said divide x minus 2 to both sides. And there we go, there's our inverse. Y equals to x plus 1 over x minus 2. Alright, and that's your inverse function, where you cannot have 2. X cannot equal 2 because why? Well, you should have said because you get undefined there. Alright, so let's check that. Okay, here's your, we're going to use f of inverse of f of x. So the inverse, we're going to put we're going to cut the x out of each one of those, and then we're going to put the f of x in there, 2x plus 1 over x minus 1. Okay, so let's back up for a minute. Alright, so let's see what that looks like. Alright, so we're going to put in here f inverse, and so we're going to cut that x out of each one of these x's here. We're going to cut them out. We're going to put parentheses there. Okay, so we put parentheses there, and so where that x is, we put parentheses there, plus 1 over, and where that x was, we put parentheses there, minus 2. And now we're going to take this 2x plus 1 over x minus 1, and we're going to put that in where the x was. So this would be 2x plus 1 over x minus 1. Rewrite that. 2x plus 1 over x minus 1. We're going to put 2x plus 1 over x minus 1 here. And this is just going to be just f of x here. Well, we got to get rid of that denominator, right? So what do we do there? You should have said that we're going to multiply something, right? We're going to multiply something over something. You should have said we're going to multiply the x minus 1 over x minus 1. And then we're going to distribute that, right? So that'll be 2x plus 1 over x minus 1 times x minus 1 plus 1 times x minus 1. And that's going to be over, and we're going to do the same thing here. We're going to distribute it there. So this will be 2x plus 1 over x minus 1, and we're going to multiply x minus 1 there. Plus, and then this will be a minus 2 times x minus 1. Okay, so the x minus 1's cancel here. And so all we're left with is just 2x plus 1, and then this will be just x, distribute the 1, and that's just plus x minus 1. And so the x minus 1's cancel here, and we get 2x plus 1 minus, and then we distribute that negative 2, right? It becomes minus 2x plus 2. Okay, so now let's see if we can, what can we cancel here? Well, the minus 1 and plus 1s, they cancel, and you got a 2x plus 1x is a 3x. Okay, and now here we've got a 2x and a minus 2x, they cancel, and you got a 1 plus 2, and that's 3. Well, here the 3's can cancel, and you're just left with x, and yes, it checks. The two are inverses of each other. Okay, and that's what we did here. And we know that x cannot be 1 here for f of x, and we know that x cannot be 2 there for the inverse.